Hello, Chem 22 students. This is Dr. Klein with another lecture installment with examples. Here, what we're going to try to do is determine whether each of the following compounds or ions is aromatic and also justify our choice. And again, I've written out the answers in advance because I've learned that that makes life simpler. So for the first one, we have this cyclopentadiene anion. This compound is aromatic, and that's because the carbon with the negative charge rehybridizes from sp3 to sp2, and that way the lone pair can end up in a p orbital, and that provides a total of 6 pi electrons. And this particular ring is going to be planar as long as the carbon with the negative charge is sp2. So again, we have a planar ring, 6 pi electrons, continuous chain of sp2 hybrid orbitals with one unhybridized p orbital each, and that makes this first compound aromatic. The second one looks really weird and really unstable, but it turns out that it's actually pretty stable. And at least based on aromaticity, this particular molecule is going to be aromatic. It's planar, it has no choice. It has 2 pi electrons, and that fits the pattern of 4n plus 2. If n equals 0, which again seems a little strange, but there you go. So now we move down to this compound, which is the anion of a triene. And it's useful to compare this to number 1. So here we have a total of 1, 2, 3 sets of pi electrons. So that's 6 pi electrons. If the carbanion carbon were to rehybridize and put the lone pair in a p orbital, that would give us 8 pi electrons. We don't want 8 pi electrons because the only option for 8 pi electrons is anti-aromatic. So as a result, this thing stays sp3 hybrid, and the lone pair is in one of those sp3 hybrid orbitals. Therefore, it doesn't contribute towards aromaticity. And in fact, you can think of the sp3 hybrid carbon as kind of being a firewall or a barrier to aromaticity, because you have to have an unbroken chain of unhybridized p orbitals. This is non-planar, so the molecule is simply not aromatic or non-aromatic. This compound, number 4, is pyridine. Pyridine, besides smelling really bad, is aromatic in the electronic bonding sense. The molecule is planar, like benzene, and this nitrogen, even following the simple rules from the beginning of Chem 21, is sp2 hybrid, and the lone pair on the nitrogen doesn't count towards aromaticity. And if you look at this blow up here, you can see that the lone pair on nitrogen is out to the side of the ring, and therefore it's not aligned with all these other, or just the p orbitals, and so it doesn't count towards aromaticity. So that gives this molecule 6 pi electrons, and it's aromatic in more than one sense. This next molecule is very analogous to the first compound. The only difference is that here the lone pair comes from the nitrogen and not from a carbon with a negative charge. And so this too is aromatic. It's planar. The nitrogen has a reason to rehybridize from sp3 to sp2 so that it can delocalize the lone pair via a p orbital. If you hear a clicking noise, it is my cat who for some reason wants to go out into the rain. And as I noted here, this is isoelectronic to number 1. We have 6 pi electrons, including the ones in the lone pair. And you can compare this diagram to the other diagram. So now the p orbital in which the lone pair is located is parallel to the other p orbitals and therefore counts towards aromaticity. So we have 6 pi electrons. The molecule is aromatic. Moving on to this compound, sometimes students find this difficult, but another way to look at this is to consider the resonance contributor. And so if you make this resonance contributor where you put a positive charge on the carbon that's attached to the oxygen, now what you have are 1, 2, 3 pi bonds, so 6 pi electrons. You have a so-called empty p orbital on this carbon, and therefore if you look at this resonance structure, and this resonance structure is going to be a significant contributor because it results in aromaticity, we have 6 pi electrons, it would be planar and therefore aromatic. The 7th compound sometimes drives students a little crazy because they're convinced that after what we've done before, they can take these lone pairs and somehow put them in a p orbital. But that's not going to do us any good here. And the reason that it's not going to do us any good here is that if we take one of these oxygens and rehybridize it as sp2, and put one of the lone pairs in the p orbital, we're still going to have this oxygen as being sp3. And so again, we don't have that continuous loop of empty p orbitals, or filled p orbitals for that matter. If we put and make both of these oxygens sp2 hybridized, then we would have a total of 8 pi electrons, and there's no reason to do that. So there's no reason to do just one of the oxygens because the other one would be still block it, and there's no reason to do 2 because you have the 2 pi electrons. Then, so that one makes that just non-aromatic, not planar probably either. So this molecule with 2 heteroatoms in it is aromatic, which I forgot to put a wavy line under. The nitrogen is sp2 hybridized with a lone pair in sp2 and a p orbital that's used for pi overlap. So this lone pair doesn't count towards aromaticity because the lone pair is out to the side. On the other hand, the sulfur is going to rehybridize so that it puts one lone pair in an sp2 hybrid orbital where it doesn't count for aromaticity because it's out to the side, and then a second lone pair in the p orbital. So that gives us what I've highlighted in yellow in this structure. We have a 2, 4, 6 pi electrons. That gives us 6 pi electrons, and therefore the molecule is aromatic. And I tried to draw this over here. Now you see why I'm not an artist. And so again, I've shown the p orbital on the sulfur and how it interacts with the other p orbitals around the ring. And you can see that the lone pair on the nitrogen is kind of out to the side and therefore is not contributing towards aromaticity. And you could do the same thing, I will attempt, with the other lone pair that's on the sulfur. So again, that makes this particular molecule aromatic. Number 9, the Cyclopentadiene is not aromatic. This is actually one of the few examples of anti-aromaticity. It turns out that molecules that are anti-aromatic are so unstable that molecules will do anything they can to be anthropomorphic to avoid being anti-aromatic. But this one's pretty stuck. It's got to be planar. It really has no choice with that four-membered ring. It can't really bend or twist. It's got the 4 pi electrons, and so therefore it pretty much just has to suffer. And so this is going to be an example of anti-aromatic, and I should have made more of a frowny face than a neutral face. And kind of to compare it, we can look at this molecule, which looks similar. It has 8 pi electrons, which fits the pattern of 4n, just as the one above it does. But now this molecule turns out it has some choices. Since it has 8 pi electrons, it would make it anti-aromatic if it were planar. But being anti-aromatic is so bad that the molecule assumes what we refer to as a bathtub shape, just to avoid being anti-aromatic. I attempted to draw it here. There's a better picture in your book without the quite so strangely long carbon-carbon bond. So anti-aromatic is so much worse than not aromatic that this molecule forces itself into, as I said, this bathtub shape, so it twists. And when it twists, that makes the p orbitals that are on all the ring carbons no longer parallel, and therefore, since they're not parallel, the molecule can't be aromatic, and so that makes this one, again, non-aromatic as opposed to anti-aromatic.